In Australia now, there are a couple of mines where the trail track from the mine to the port is autonomous. So there's no driver on those trains. You just, the whole trucks actually go and dump the ore into the right spot. The train carries them and to the port. Underground mining is pretty big in Australia. That's why I'm talking about mining. Underground is a little bit harder because no GPS. So you got to work out some other way of working out where you are. But on the other hand, driving underground in an underground mine is easy because you have tunnels. As long as you follow the tunnel, you can get to from one place to another. Say, for example, here, these are junctions in the tunnel. Actually, this bit is a continuing tunnel. It's not drawn there because the robot sensor hasn't seen it. So there's a tunnel going this way, there's a tunnel going that way. So if you're going from here, what I do is that go to the first junction, don't turn, and then go to the next one and then take the left, and then go there, continue on the left, go to the other one and take the right. And that will end up to where you want to go. So you can see that the control strategy is still not that complex. It's relatively simple, but it's again, these trucks are big, they almost fit the tunnel. So controlling them is hard, and they are again really heavy. If you stand up to about here. So they're huge machines. And also in some mines, there is a danger of explosion. There can be gas pockets in the mine, and if you break into them while you're digging, that can blow the machine backwards, and it's dangerous. So some of the machines are actually operated remotely, like playing a video game. So this guy sits there, drives it, and it's pretty hard to drive, and they really damage them. They bash them into the walls because you don't feel anything. And you got to go fast. So there's been activity trying to automate this for a long time. Again, another maybe more than 20 years. We got involved in doing something probably even close to 30 years ago. In one of the Australian mines, and now there are commercial systems that are doing it. Because you don't have the GPS, you can't use a radar to see far away. Here you use what's known as a laser rangefinder. So it basically tells you the distances to things nearby. So let me see whether I can play this video. So this, what you see in red is what the laser rangefinder sees. It tells me that there's something this far away. And I can try and match it to the tunnel shape to work out where I am. So that's how the location works. And then the control becomes just following the tunnel and taking the right turn. So you got to, once you have the mind map, you can work out to go from A to B, just like when you put this into your GPS in Google when you drive. It tells you, okay, this is at this junction, you go this way, and you can automatically plan this stuff. So this is again, mining is a very big area where future automation it's already there, and it's growing very rapidly. Okay, this is obviously something you've seen many times, self-driving cars. This is a huge activity at the moment. This is much more challenging, because now you've driven, especially in Sri Lanka, you drive in Kandy or Colombo, it's quite tough for a driver to do it. So the way, in a motorway, it's a lot easier. Motorway driving has been around maybe even in the early 90s. There were systems that will drive on a motorway, but they'll only go to the exit, and at the exit, your driver has to take control. So motorway driving is just following the lane. And make sure you're avoiding and overtaking and this kind of stuff. But if you're in the street, it's very difficult. So the only way this can be done now is to give it a lot of information. So people like Waymo, which is a Google arm, or Uber, they go and map the environment at very dense, accurate level. So they use these 3D laser rangefinders to map everything. So all the buildings are mapped. And obviously things change. So after 6 months, you got to go around again and map. And sometimes the laser is not good at when it's heavy rain, so it's difficult. And then they predict everything. They predict everything that's going around. Sorry for disturbing.
Hello, Professor. Could you please start? Can you start the recording? I mean, we were recording, but they were lost. Could you give me the permission to record the?
I
Maybe you can,
don't have a button for record.
maybe you can use the access to me to record. If you
How
go
do I do that?
if you go to my name in front of this tab, no, as shown as more.
Let me see.
If you go to my name.
I can't really see
In the participant list. So if you just click the participant, and if you go
okay, yeah, and
then go to mine in front of my name. So there's more.
Where's your name there? Nalin.
Nalin Harishchandra.
But Nalin, I can't see Nalin. Your name is not up. Maybe it's come up to. There it is.
Yes. Okay. Then if you click the more, maybe
more. Yeah. And then
is there something to give permission to record or something? No?
There's nothing allowed to record. Yeah. Okay.
Okay.
Got it.
Okay. Thank you. Okay.
All right. Sorry
for disturbing.
That's okay. All right. So self-driving cars. So you map everything. I mean, you can see in here, they work out where all the cars are, try and predict where they're going to be. If you're driving a car here, you're not going to worry about what this guy is trying to do over there. Because we are very good at reacting to the environment and plan even when we don't know exactly what's going on. This is known as planning under uncertainty. How to do it well is not in an autonomous way is not easy, and we really don't know. So here the challenge, the strategy is to reduce the uncertainty as much as we can. We try and work out everything, and we know what this car is going to be, where this car is going to be after 20 seconds, and we try and predict where this one is going to be after a certain amount of time. Once I know that, I can plan, but if my prediction is wrong, I'll run into trouble. So I got to be able to keep predicting over and over again. So you need a very fancy computing strategy to do it, except we do this by being able to predict, plan under uncertainty. I wait. I mean, when I drive here, I expect this person to do the right thing and do whatever the road rules say. If I was driving in Sri Lanka, I expect this person to do something. I watch them carefully to make sure that I don't run into them. So we are very good at this, and this is still not there. Now, this is a technology we really can't get into at a university, mainly because a lot of companies are putting lots and lots of money and hiring lots and lots of people to do this work with a lot of resources. So recently we've done something which is quite interesting, using this kind of technology put it into a slow-moving vehicle, a mobility scooter. It was actually done by a student from Peradeniya. It's my last PhD student. I'm retiring in a month or so. So so Malin is the last one I'm going to graduate in. So what we tried is, so this is a mobility scooter. People use it for, typically used by aged people to drive around. It's like so here you lose your license after a certain time if you can't, so you're not allowed to drive. If you fail your driver's test, they do it, you have to do it every year. Hello? Are you recording or you're right? Okay, so what we've done is to try to use what it's a very simple sensor package to work out how to work out where it is. So what we do is we look around and we try and recognize things that are in the environment. We try to recognize trees, light poles, street signs, parking meters, and things like that. And these are done using deep learning, AI. Deep learning has become an integral part of robotics work, and I can see more and more into the future. We'll be using them to understand the world around us, which has been a big problem in robotics. So now there are very clever algorithms that can do this sort of thing. So we work out these things, and I'll show you a video. So this is a mobility scooter. It's got this spherical camera so that I can see all the way around. I look around to detect whether there are poles and things like that. I look on the floor to see the edge of the floor, see whether there are manholes and things like that. And we use that to work out where the vehicle is. We know where these streets and poles are. We know where the manholes are. So therefore, if I'm driving along, I can use this information to work out where I am. And if I know where I am, I know where I should be because I should be on the path. I can come up with the driving strategy to be on the path or avoid people on the path. And if I have a map, I can work out how to get from A to B. And at this point, we only do localization. Control and mapping, so control and planning is another step into the future. So I think the self-driving cars are still not there yet, but they hopefully be with us. Hard to tell when, because there's a lot of hype rather than reality with self-driving cars. But that's what it is. Okay, I think I'm running short of time, so maybe I'll try another 15 minutes and stop. So I'll quickly go through them. Another big area which is currently people are trying to really work hard on in this indoor environment, especially in commercial spaces like shopping malls, hotels, and so on. And there's been huge amount of investment in this space. So this is kind of what happens. In the factory and warehouse, there's a lot of structure. And the robots have been very successful there. This is a shot from an Amazon warehouse. If you buy anything from Amazon, these little orange things are robots, and these are the stacks where their parts are. So the robots actually move the stacks around to the people who are picking things from those stacks and putting into your boxes. So robots still can't do the packing for you. So when you order something from Amazon, most likely the parts actually got to a human in some spot using a robot, but that person actually picked it up and put them into a box and covered it. And then it probably got shipped. The other end is at home. It's much less structure. Nothing's been really successful in that space except vacuum cleaners. So robot vacuum cleaners have been around for a long time. There the challenge is that the interesting thing is that it doesn't matter whether they work or not. Whether they hit something, you just run around. It's very small number of failure modes in there. So you can build one cheaply and it will go around and clean it. And if a little bit of the room doesn't get cleaned, it's not a big deal. Unlike here, if the right piece doesn't get to the operator, then you have a big problem. Halfway is these semi-structured things like that. And here is a view of so many robotics companies setting up to do this. But they're finding it really difficult to make any dollar out of it. It's still not as easy, and the know-how is not there. So this is hopefully coming in the future. So these people, Bossa Nova, working with the big American company, Walmart, which is a big storehouse there, and to check the inventory on the stacks. And recently, just last month or two, the Walmart has decided that this is not good enough. I can get a person to do it. These things still can't pick things from a stack, and just like you do, you can go to a stack and pick what you want in the supermarket. These things still can't do it. They're still not good enough to go and put stuff into the stack. Give him a stack of things, you give it to a person, he or she will go and fill the stacks up, and they still can't do that. But this is the challenge people are working on. Hopefully, it's reasonable to think that this is possible. Doing it cost effectively, fast enough is the challenge, and I think people will gradually get there. This one, I think, okay, underwater inspection is another example where it's the robot that move around, take pictures, and try and compare one bit of the reef to another after 1 year. It's got to recognize that it's in the same spot. So what happened to the coral? So this is one of my former students actually at Sydney University is running this work. We built a robot to inspect an arch of a bridge. So this is Sydney Harbour Bridge. It's got metal arches that are actually whole. It's a box section, and you got to go in here and inspect it to see whether it's rusted. And this is what you used to do. You crawl into them, and this is not allowed by law anymore. We can't put a person in there because it's not safe. It's not safe. So we built a robot based on this idea called inchworm. So these are worms that actually have these two ends where they get stuck into the wherever they want to go to, and then move like a leech in Sri Lanka, actually. So it's the inchworm. So we built a robot based on that principle. It's one of my colleagues and myself and another professor who got involved in. So I'll show it to you quickly when it comes. Okay, so it's got magnetic feet at the two ends. So because it's a steel bridge, the magnets can be enabled to get stuck to the wall. And once you're stuck, you got to look around and work out what's around you. So it will build a map, and then it do motion planning, plan how to go from A to B. I don't want to be stepping on rivets. I can step in the places where there are less rivets. I want to go through that hole. So I do the planning. And once the planning is done, then you got to execute it. So it's got an user interface a person can put in there, and then it will basically run. So this is how it comes in. So it's the real machine. So it looks around, build a map, put the foot down in the right spot. It knows that there are no rivets there, and then look around again to work out where can it put the foot. So it looks around and put the foot, and it will also take images at the same time to show it to an inspector later on. It will store them. So it does the motion planning, it records everything, and then it executes it. So it can go in and go into the next chamber through the manhole. So it can currently navigate across 2 chambers. And then if you want the rest of it, you got to go and put it in from another manhole on the other side. So it went in there, it will still examine it, and then it will come back to get out of here. So it's an inspection. It doesn't do anything except looking around. Similar example in a concrete bridge. Concrete bridges have these holes inside to reduce its weight. So it still keep the strength. So that cavity needs to be inspected. Now this time it's concrete, so you can't use a magnet. So we have a tracked vehicle doing that. So we build this robot to go in and again take pictures. Another example, water mains. Australia has a water infrastructure which is probably 100 years old. And a lot of these pipes are built of cast iron. And cast iron corrodes, or any iron corrodes once it's buried in the ground. They're about 1 meter underground. Once they corrode enough, cast iron is brittle, so it breaks. It blows up, it explodes catastrophically. So we built a robot to go into these pipes and map the wall so that somebody can tell you, you can analyze it, the engineers can analyze it and see, okay, how long can it last? So this is one of them. It got these electromagnetic sensors to measure the pipe wall, and it just drives in. So currently our students actually do this on call. So we pay them to go out and deploy these robots when Sydney Water calls us. So it goes in, you go in, you put the robot in, go 100 meters, come up with a map, and then show it to the site supervisor. And if the spool next to the break is damaged, they'll remove it. Otherwise, they'll bring it back, and the engineers can do something about the pipe if they find that it's really badly corroded. We've got another one which has a 500-meter range, so we can actually examine 1 kilometer of pipe from any entry. But all this has to be done without water. So now we're actually building a robot that can go into the pipe without shutting down the water, so without disturbing the customers. That project is just starting, so that's probably the last project I'm going to be doing with this team. So I'll be staying on at the university as an honorary just to complete that work. Hopefully in a couple of years we'll have it running. So here is another, here now everything is inspection. So far you've seen inspection. How about robots that do some work? So here is an example where some work is happening. This is what is known as grit blasting. It's a common industrial process, mainly to prepare surfaces of painting. So this is Sydney Harbour Bridge. So when you're if you want to repaint, you have to take the old paint out, and then you put the new paint. This is a very hard job. The force at the end of this is about 10 kilos or 100 newtons. And you got to do it, you got to apply 100 newtons all the time. with different postures. So it's really back-breaking work. So the Roads and Traffic Authority came to us and asked us whether we can think about building a robot, and that's this video. So it's the Sydney Harbour Bridge, an iconic thing in there. So lots of steel, and the paintwork has to be gradually managed. So gradually they start from one end and start take the paint out, repaint, and go on. So this is how the robot works. It goes into the area where the painting needs to be done. The operators put it on the floor. And then again, just like as I said before, first sense the environment. Look around to work out what's around you, because you're not in a very precise position. So I got to map everything. It moves in a intelligent way to maximize the coverage. It doesn't need to see everything because we know how the bridge looks like roughly, but all the panels are different, all the dimensions are different, but we know the shape. So we use that knowledge to build up a map of where it is. So okay, I know what's around me now. Now I know the task is to clean, so I have to do motion planning. So there's an algorithm we have there. We take the map and we do motion planning. So it pans the paths for the robot to move so that the whole surface gets clean. Once it's done the planning, it actually animates it and show it to the operator. And then operator, when the operator is happy, they say go. So there's always a little bit of human interaction there, mainly because the robot cannot do 100%. It can't clear everything. Some corners we can't get to. It's not worth the effort building a system that does everything. So what we've decided to do here is let it do maximum it can, and then the operator who was watching it will go there and fix up the rest and get rid of the bits that are missing. So the operator see it as a support aid, and it makes their life a lot easier. They're not carrying that load for a very long time. They're watching it most of the time, and then just go and does whatever they have to do. But their job is still there. They're not replaced, because without it, you need the person. I'll probably talk for 5 more minutes given the time. So here is another example where these are bridges with these pylons. In an estuary, there a lot of marine growth happened there. So there's a lot of this stuff. And because it's concrete, you got to inspect it. So what happens is normally a diver goes in and cleans it up with the water jet. So you can see this diver doing a water jet, cut a stripe, and then you take photos of that stripe. And that's how inspection is done. So it's a sampling exercise. So divers, it's a hazardous task, and diving is not easy. So we've actually got asked to build a robot to do this. So we have a robot that actually sprays the water. So let me skip a little bit forward. Yeah, so this is the robot. So maybe hopefully we'll see. So it's got these hands that can go and grab into the pylon. So it can deal with different pylons. And it's got a camera to map the environment. It's got the claw arms, and it's got this water jet. This one can actually move. So we'll see it operating in here. So it's this is in an estuary. So it goes in, grabs the thing, maps the pylon. So it's now got hold of the pylon. It does a map. It knows what's around. It plans what to do, and then it executes this by firing a water jet at this thing. So now it's actually firing the water jet to clean all that marine growth. And once it's cleaned, it will take some photos and bring it back. So that's been an interesting project we've done some time ago. Okay, maybe this one. Okay, so that's the robots that work. But what about, can everything be done by a robot on its own? It's difficult, mainly because of the level of planning and intelligence, as I mentioned. So assisting people to do things is becoming more and more into the future. Even the driver assistance systems are much more successful than trying to do self-driving. So here we're actually looking at a system where where you can't really build a robot to do all this because the tasks are very different. It's much easier for a human to plan the paths to do it because I look at it and I can do it. But the force is the important thing, which is hard because of the 100 newtons hitting you all the time. So here is a system where a person drives the robot and does the task, and the robot takes care of most of the load, and the person tries to do most of the planning. You got to be a little bit clever here because if you let the robot do everything, the person will kind of lose interest very quickly and may do silly things. So we provide the assistance. We call it assistance as needed. We just provide enough assistance to help the person, but not too much to make it too easy. To do that, we monitor where the person is, where his or her hands and legs are, do some biomechanics to work out what kind of forces. So if you're trying to blast on the top, we provide more support than if you're trying to blast something in the front. So this is an example of the next type of work where robots and people are working together. And I think this is becoming more and more useful. Say you've probably seen about robot surgery. A robot helps a surgeon do some task. The robot is not good enough to do it on its own. It just provides the support to the surgeon to be able to do the task a little bit more safely and a little bit more easily, like eye surgery or things like that. So there are robots around now to do this kind of thing. 2 minutes to go. So humanoids, I haven't done much work in humanoids. Humanoids have come a long way. So these are things with legs, like people from maybe this is like in the 80s, where you had a big umbilical to support it and it moves so slowly into something quite sleek like the Honda. But there's still the intelligence level of these things are not great. So if you look at this thing called DARPA Grand Challenge, which was done a couple of years ago, you see a lot of videos where all these things fall down. In the end, the robot so what it had to do is to get off a truck. The competition was to get off a truck, walk up the stairs, open a door, and close a van. And so many robots fell down, just couldn't navigate. Because now, not only you got to look at the environment and react to it, now you got to worry about your balance. And you try to move too far, it's still challenging. So the one that won't actually kneel down to move. So it's a robot, it's legs and wheels. So it kneels down and then it doesn't fall down, it moves fast. Also, although, I mean, having said that, there are some very nice machines, leg machine that can do it. This is Boston Dynamics. I'm sure you've seen this video. So they move very nicely. They're very nicely mechanical designs. And there's the robot dog, the 4-legged thing. So the actuation side is pretty good. The missing bit probably is the perception, how to work out what's around you and do stuff. Still, there's a lot of good things can be done. This talk is not going to be complete without talking about drones. So here, drones are now getting used to deliver takeaway food. So in Canberra, in Australia, and in Queensland, Logan, there is Google Wing actually delivers parcels to, you can ring up and ask for a takeaway food, and the drone will come and drop it into your backyard. So actually, one of my former students who's from Sri Lanka, who graduated, and he now works for Google Wing. So I got some interesting information from him actually. They are more in humanitarian effort as well. So this is a trial that UNICEF is running with one Australian startup to deliver vaccines. So this is there's the roads are that difficult to get through. You have islands, and then vaccine has a limited lifetime out of the freezer. So you got to fly them quickly, and they are doing that over there. In Rwanda, there's these robots that are actually doing moving, collecting blood. So these more and more robots are coming into humanitarian effort. More and more robots are coming into, as Nalin mentioned, disaster rescue and this kind of scenario. So this is probably where I'm going to stop. I've hopefully given you some insight into what we've done and what's kind of happening, and a little bit hopefully into the future as well, although I admit not too much. It's predicting the future is pretty hard. I wouldn't have predicted some of the things in self-driving if I got asked early 2000. Okay, so this is where I stopped. So our funding comes from the government as well as from industry. So about 80% from industry, and PhD students are the backbone of much of the work. I know many Sri Lankan students. We had many Sri Lankan students going through. Unfortunately, from now on, I'm not able to take any in because I'm no longer going to be working. Unfortunate, but that's the way it is, I guess. So I stop there and wait for some questions, Nalin.
Thank you, sir.
So did it come across clearly enough, or was the net good enough?
For me, it was okay.
But you missed the front bit in terms of recording. Okay.
Yeah, that was a problem because they were it was recorded, but the students, they were trying to put this in a live in YouTube channel. So because of that, they were recording. But after some time, it was somehow disconnected or something. That's
Okay.
why. At least now it's
so
recorded.
look, I mean, it's probably difficult to manage questions, but I'm happy to. I mean, I have time. It's night here, so I can wait. And if people have questions,
let's see. Yeah. Hello, everybody. Do you have any question? Of course, you should be.
Hello, sir. I'm Asit, a final year undergraduate in University of Peradeniya. My question is, sir, I see a lot of people, including myself, that have that burning thirst for robotics in the beginning, even during the school days, and we dream of practicing it throughout our lifetime. But somehow during the way, we kind of lose it, because I think we don't have something to, other than the notion that we should do robotics. We don't have a solid plan or a goal.
It's not different here. It's not different here. Undergraduate days, we try and run some projects related to robotics with students. And but we have subjects, but there's not a lot there. In some of these industry projects, we try and we have a thesis. I'm sure you have a final year project there as well. And for this final year project, we try and use students join the industry projects, and therefore they get the exposure to it. But normally, after that, people tend to come to postgraduate studies, and that's where they really learn this stuff. Or if they go to industry with the company that is working in robotics, they learn. So I think as an undergraduate, you get the basic ideas, but and hopefully do some projects that involve robotics. But beyond that, it's difficult. So, I mean, our mechanism for engaging students is projects. We try and run projects, and we try and encourage them to join industry projects, so they get the exposure to both industry and robotics.
Okay. And so when you are selecting your postgraduate students, if I'm to apply for postgraduate position in a robotic related field, how should I prepare for it?
Yeah, look, I think, it's the interest is the most important thing. So normally, we don't, like when I went to do robotics for my PhD, I knew nothing about it. I did conventional mechanical production degree, and that's the end of it. So when I did it, actually it was mainly mechanical. We had 1 year of production engineering, but it's mostly mechanical. It was the very first batch with the production team. So there was no robotics there. Robots were not around at that time, but I ended up doing it. So I don't think But nowadays, if you want to do robotics PhD, you really need to have that knack. So if you're an electrical engineer, knowing a little bit of mechanics is a good thing, because you already have the electrical and probably the software background. If you're a mechanical engineering student, knowing a bit of electronics and computing is a good thing, because you probably need that. And many of our PhD students, we expect them to be good in maths, because a lot of the background work, a lot of the theory stuff is estimation. I mean, at least I'm in estimation. So estimation, statistics are important. So it's a good, I mean, my philosophy is that if you're a good undergraduate student, then you should be able to adapt into one of these, provided you have the basic, these basic things. For us, it's a bit different because we have mechatronics students. So they have that, they have both the electrical and mechanical knowledge. But when we get students from overseas, and Malin is an electrical engineering undergraduate. Yeah, so he's very good at robotic stuff now. So he's from Peradeniya, I think. Maybe graduated 4 years ago or something. So I have few people from Peradeniya electrical and Moratua electrical and computer systems engineering schools. No one from mechanical actually. Although we are a mechanical engineering school. I'm a mechanical engineer to begin with. So yeah, look, I mean, the background, I'm not too worried about. I think, you got to have that interest and have done something.
Okay, sir. Thank you very much.
Hello, Professor.
Hello.
Yeah, I have a question. Okay.
All right.
So when you do this, when you start, I mean, to build a robot, so how do you start with the straight go to the hardware implementation, or do you start with simulation? So if you have any kind of software.
I mean, we do a bit of simulation. The design. Okay, so we don't normally go and build a robot for something unless there's some very specific requirement. Like, in the industry project, we have been given the problem is in front of you. So you're thinking of how to solve it. So then you need to think about what are the things necessary. So normally we will say, for example, in the bridge robot scenario, we built a sensor package first, put some sensors together and move it around inside. We build a mock-up of the bridge structure in the lab, and we moved it around to see how to build this map of the environment. And then we worked out how to do the motion planning. And then we actually bought a robot. So we try and buy as much as we can. We initially just bought a robot, and we put the sensor package at the end of it and do it. And then, it's a combination of things. In the mobility scooter thing, we thought this is an interesting problem. So it's a PhD problem. It's no industry. So we say, all right, we are going to, we again put a sensor package on something and move around in the lab to see what we can do. And then we bought a scooter and put the sensor package on it and driven around. After that, we sort of integrated into it, and we still haven't got it connected to driving. We just still somebody's driving it and we are collecting information. So in the water robot, we initially built sensors first and tested how well they work on steel and cast iron, see whether we can detect thicknesses. And then we designed the robot to stick those. So it's we do a bit of simulation in terms of system design to test things during the software development. We do a bit of simulation. Mechanical design, we do a bit of simulation, but yeah, we tend to, industry projects, we tend to build them. In research projects, we do a lot of simulation.
Yeah.
Because then, you don't have a system you can really run. Or experiments are hard to begin with to cover everything. So when you do research, you need to see how. So currently, fortunately, there are a lot of data sets around in the world, in the community. I want to test something, I can find a data set. Somebody's built a robot and put a sensor package on it and collected it. So normally we use the existing data set, then it's easy to demonstrate that your algorithm is better than somebody else as well, because you can compare. So yeah, it's a combination. We do simulation as well.
So I have another question as well. I'm not taking too much time. So how about when the robots are kind of supporting the human actions? So what will be the loads? So as I said in the previous, when they are in the assembly line, so it's, the load is not to put a human.
Okay, so with robot working with the person is challenging, mainly because if there's in an environment, if there's no people, we know where things are. Everything works with geometry and Newton's law, right? So you know how much force is required by that blasting gun, and if I have enough force and I point in the right direction at the right distance, it does what it has to do. Once you put a person in there, you can't predict what a person is going to do. There's no real good model of this person. If it's another robot, I can build a model for it. I can observe it and work out what it's going to do. But human, it's difficult. So this is a really difficult challenge in robotics, human-robot collaboration. How do I understand what a person is trying to do, and how do I communicate? Or as a person, how do I communicate what I want to do to a robot without actually having to type it in or talk? Like if I'm in front of you and I put my hand towards a water bottle near in the middle of a table, you quickly recognize my intention. He's looking for water, so you will pick it up and give it to me. Can I train a robot to do that? It's very hard. So yeah, doing collaborative tasks is difficult. So how do you share the load? It's a good question. I mean, so in that example, we basically we have some notion of what the human can impose on what's the load human can take without actually getting really tired or without being hard. We have a simple biomechanical model. So depending on the posture, I can compute that having say 100, say 20, 30 newtons at this place is not difficult. So we try and provide just enough force to the human and take the rest by the robot. So the human stays interesting. That means if the human lets go, the work doesn't get done. It's not too easy, but it's not too hard. So it's always a compromise. I mean, sometimes we do something simple and say, okay, 10% of the load to the human, 90% to the robot. But who decides 10%? It's arbitrary.
Okay.
It's difficult.
Thank you very much, Prof. Thank you very much for the interesting talk. So,
okay,
over to you, Primesh.
Thank you, sir. And thank you very much for you, Professor Gamini Dissanayake, sir, for your insightful speech and for sharing your experience with us. And I hope everyone gained some knowledge about robotics project and currently developing and the fields that will transform into robotics in the future. Now I would like to invite Mr. Asita Devinda, Secretary of IEEE RAS University of Peradeniya, to deliver the vote of thanks. Asita, yeah?
Thank you, Ali. On behalf of the Robotics and Automation Society of University of Peradeniya, I'd like to thank today's speaker, Professor Gamini Dissanayake, for spending his valuable time to provide us with such great information and guidance on robotics. Today's session was extremely interesting, sir. And given the time of the day, everybody, I think I know most of the time everybody is sleepy, but today, speaking of myself, I was wide awake. It was that interesting. Your exceptional knowledge as well as your great delivery made it an informative and extremely interesting session. I'm sure each and everyone in the audience thoroughly enjoyed the session and had their thirst for robotics rekindled. I also like to thank Dr. Linan Samaranayake and Dr. Nalin Harishchandra for helping us organize this evening. Finally, I'd like to thank all who joined with us today to share this great moment. I hope you'll stay with us in the future programs as well. So thank you everyone and have a great evening.
Okay, thank you very much. It's my pleasure. It's good to do something back to our where I graduated from to Sri Lanka. So I was very happy to do it. Thank you.
Thank you, sir.
Thank you, sir.
Thanks.